Okay. So, let us look into link state protocol, and let us first define some of the syntactical things that we may require, right. Uh, so, each router knows the state of all the links and the routers in the network. Okay. So, what do you mean by state? The state of a link could be whether the link exists or not, first of all, if the link could be down also, right, and also you can assume the weight of that link. Okay. The weight of the link or the cost of that link should be known, and that is known by the routers in the network. Okay. Each router in the network, and same for the routers also. The routers could also be down. So, if a router is down, then the links that are associated with that router are also going to be down. Okay. Every router performs an independent computation on globally shared knowledge of the network's complete graph representation. Okay. So, this computation that is happening on a given router is independently done for all the routers. Okay. So, the computation is common and the information that is shared is global and same to all basically, right. So, the network's complete graph representation is going to be there in all the routers, and the routers are going to do some kind of a computation. What is the kind of computation I already discussed, right. So, you typically are going to use this network graph for routing, and what is the main point or what is the main purpose of routing? To figure out an optimal path, optimal in terms of cost, right. So, you essentially need to figure out the shortest path in a graph. Okay. And if you are a certain router in that path, you should be knowing that what should be the next hop you should forward the packets to. Okay. So, that is the main goal of a router, or the main functionality of a router is to forward packets through the appropriate router ports. Okay. Do not lose connection with the original intent of routing and what routers do. Okay. Here we are going to look into more into graph algorithms, but essentially the problems that you are solving is packet forwarding through a appropriate output port of the router, and your all these things, this is basically going to solve this problem, that which one of the output port you are going to use for a certain destination of the packet. Okay. So, there are two things that we are going to look into. First is the part that is associated with flooding and information exchange to get the complete representation of the network graph. Okay. So, we are going to use this example that is shown on the right hand side, where U, V, W, X, Y and Z, these are the 6 routers. Okay. And note that we do not have a link from every router to every other router. Okay. So, there are a few links, right, that are marked with this black straight lines connecting the routers, and the numbers represent the age weights or the link costs. Okay. But this is the complete information of the uh, network graph, which is unknown to the nodes. The nodes do not know. Okay. The node somehow has to be conveyed this information, that how the network graph looks like. Okay. So, there is a first thing that that is done at the initialization is something called link state flooding. Okay. So, this is a process by which the neighborhood information of each network router is transmitted to all the other routers. So, a router, for example, let us say router V, it has these neighbors U, X and W, right, and V knows that I have a link weight of 2 to U, 2 to X and 3 to W. This information is something that you can share with your neighbors. Okay. So, in that way the neighbors would be able to get an idea of the graph subsequently, okay, because this information goes everywhere, and people could stitch together, or rather the routers would stitch together this information to get the global view of the network, okay. So this is transmitted, this piece of information is transmitted to all other routers. So this is something which is called a link state advertisement, the link state advertisement or LSA to each one of the neighbors. So I gave you this example of router V. So V is going to send it out to U, X and W. The LSA contains the router ID, the IP prefix owned by the router's neighbors and the link cost to those neighbors, okay. So if you remember the discussion earlier we had about this local networks, NATing, and then this global IPs and so on, right. You are not really going to list out all the nodes that are there in the subnetwork of V, right. So V is basically going to be identified with a network prefix. So any node which is destined to the network which is behind V is going to go through V, right. So there is no necessity to have a routing which is based on individual network IPs, rather we are going to do the routing based on the IP prefixes, okay. So V is going to own a certain bunch of IPs which is going to be a certain prefix, let us say some /24 network or /22 network and so on. This is going to be if you get the packet to V, then we can forward that packet to its internal network, okay. So we are going to do the routing based on the IP prefix that is owned by the router, okay. Please keep this in your mind that how this connects to the routing the packet eventually to your local network and eventually to your actual host who is going to receive the packet or who is going to send the packet, because the routing does not just end with the routers, right. Ultimately the packet has to come to the network hosts, okay. So router ID is there, the router has to be identified, the IP prefix is owned, which is owned by the router's neighbors. The router is going to have a host of direct hop neighbors to whom it is directly connected. It does not have to go through another router to reach that host or rather router, and the link cost to those neighbors. Here we are showing this example that this is UV, this is 2, VW, this is 3 and so on, this is 2 and so on, right. So these are also something that are taken into account, okay. So this is going to form the message structure for the link state advertisement. So this link state flooding is the first thing where you initialize these message exchanges to get to convey the complete network graph to all the routers, okay. Upon receiving the link state advertisement, a router forwards it to each one of its neighbors. So when X receives the message from V, okay, X is going to forward this message to W and Y and U as well, right, because it is not only receiving from V, so it may not go towards V, but it is going to go towards other nodes, okay. So that is how every message is sort of sometimes replicated and sent out to all possible nodes in the network. So making sure that every node in the network has a copy of each message, and then they can stitch them together to find out or estimate the global network graph, okay. So W does the same and so on. So eventually the entire network receives the link state advertisements originated by each router, and they put in something which is called a link state database, okay. So the link state database is going to have a collection of all the link state advertisements, okay, in each router. Please understand that this router is going to have this link state database, right, because we are going to maintain the entire network graph in each one of the routers. the LSS occur periodically and whenever the graph changes. So, why periodically? Because every now and then the weight of a link can change, right. So, there has to be a mechanism to estimate the let us say the bandwidth of the available bandwidth of the network, right, that may change, right, and uh, you really do not have any direct way to figure that out at the IP layer. Um, but periodically you can have some other mechanism to figure those things out, right, whether a particular node is reachable or not, what is the latency, right, at least using ICMP packets you should be able to figure out the latency, right. So, and latency can capture to some extent congestion, right. So, if the latency suddenly spikes up, which actually means that there could be a lot of congestion in a certain link, right. So, somehow you have to, because that is an abstraction we are making here, that how the weights are actually derived, but here the link state advertisements are going to contain the weight values. Okay. So, these are updated periodically and whenever the graph changes. So, for instance, if you have a network node that comes down, right. So, your neighbor is not reachable, at those times also you are going to send out this link state advertisement messages announcing that I do not have a link to this particular guy, that router is down. Okay. If a link fails, which is exactly what I told you right now, and if a new link or a router is added, this is also important because that is a good news that I have an extra path, right. So, there could be a new router that is added to the network which essentially creates a new link, or you can have another new link without even adding a router, right. So, you can have an extra edge in the network graph. This is also an information that needs to be shared with all other nodes because the shortest path may change now based on the weight of the new link. So, the routing algorithm running at each router use this entire network graph to compute the least cost paths. Okay. So, just think of the replica of this cloud that I have shown on the right hand side, this sky blue colored blue colored thing, right. This is going to exist in all the network nodes. Okay. And what are you going to do? You are going to compute the least cost paths. Okay. What is the shortest path for a certain source and destination pair. Now, we come to the compute part, that was the data part, which was mostly information exchange. Now, we come to the algorithmic or the computation part, and you can all guess what is the computation or what is the algorithm that we are going to study here. In a graph, if we want to figure out the shortest path from a certain source to a certain destination, we can't avoid Dijkstra's algorithm. So, here we are going to also apply Dijkstra's algorithm because the abstraction has been made now. All we have or all we care for is a weighted graph. Okay. This graph could be directional, could be non-directional as well, but that is up to the problem, right. Sometimes the cost of going from A to B might be high, maybe B is highly congested, but the cost of coming from B to A might be less, right. Maybe A has more capacity or A is less congested and so on. So, in those cases we can still have the idea of having a directional graph. Okay. So, for now you do not have to worry about directionality, you just see that take non-directional edges, but just keep in mind that that can happen and you should practice a few problems like that. Okay. So, given a network graph, the algorithm computes the least cost paths from one node to all other nodes. This is all of you know, right. So, source node is the node from which the messages originate, and what is the path that is going to be taken by the message to reach the other nodes. Okay. That is what essentially the Dijkstra's algorithm does. This can be used to compute a forwarding table at the node. So, if you know the path from the source to the destination, let us say S to D, if you know the path that what was the path that was taken for a message to travel from S to D, you can compute the forwarding table. Forwarding table means suppose you are an intermediate node I, Okay. If your destination is D, what should be the next hop I should forward the packet to? Okay. I am repeating that. Suppose after running this Dijkstra's algorithm, you see that you have a shortest path from source S to destination D, S to D, okay, and you are an intermediate router which is I, okay, in the path. Uh, your main task is to populate the forwarding table. What is a forwarding table? When a message comes, I should be looking at the destination, I should be able to forward the packet to the appropriate router, okay, through my appropriate output port. So, I should look at the message or the IP header, for instance, it is going to see the destination is D, and by looking at the destination D, it should be able to select the output port that connects to the next router in the path. Okay. So, if you had I, J, K followed by D, so you know D should have a preceding node of K, K should have message should come from J, and J knows the message should come from I. So, I should be forwarding the message to J, right. So, in this way you should be able to construct the forwarding table. We are going to look at again forwarding table construction after we run the Dijkstra's algorithm again. This is just to give you a high level idea of what is going on. This is an iterative algorithm. All of you have taken some amount of data structures algorithms class where you are taught graph algorithms, I guess, right, at least the shortest path. So, you know that it is an iterative algorithm, and it at every step, right, we maintain the least cost path to some of the nodes, right. Specifically at the kth iteration, each node definitely knows the least cost path to k destinations. Okay. So, so this is once you exhaust all the nodes, then you know the shortest path to your required destination. Okay. So, it is an iterative algorithm where the data is maintained temporarily, right. So, you have a certain belief that to reach a certain destination D, this is my shortest path, and that belief gets updated over time. Okay. We are going to see or rather revise how exactly it works. There are a few notations we are going to use because we are also going to stick to this notation for your exams or the assignments that are going to be given to you. So, the notations, and the first notation is this concept of cost C, C x comma y, this is the link cost from node x to node y. If you do not have a direct link connecting these two nodes, we can note that or you can actually annotate it using infinity if they are not direct neighbors. So, the edge does not exist in between x and y. There is dV. dV is the current estimate of the cost of the path from the source to the destination V. Okay. So, if you initially you may have that cost would be infinity, there is no direct path, but with the iteration, with time, as we go through the algorithm passes, your estimates are going to change and going to be updated over time, and ultimately you need the best estimate, right. So, we are trying to minimize this this dV, we want to minimize that, but in an intermediate step of the algorithm, we are going to have a current estimate of the cost. Okay. So, that is termed as dV. So, dV is the current estimate of the cost of the path from the source to the destination V. There is one more thing that you need to know, which is called the predecessor node, the last node before V on the path from source to V. So, as I told you earlier that I, J, K and so on, right. So, in a certain network path, the predecessor node is basically the node preceding the node in question. Okay. So, PV is the predecessor node of node V, right. If I told predecessor node of node J, it would have been I, right, in based on the example just I had right now, just the previous node. Okay. So, nothing complicated. Then there is a set which is called N prime, which is a set of nodes whose least cost path is definitively known. Okay. So, as I told you that as we go through the passes in the algorithm, we have an idea of the current estimate of the cost of the path, but it may not be the optimal path. Okay. So, for a certain destination. So, we are going to as we go through the passes, some of the nodes are going to be uh, put in this set called n prime. The path through to those nodes, right, are definitively known to be the least cost path. Okay. So, you are sure about them, that some of the nodes, as you can see, that after k iterations, each node definitively knows the least cost path to the k destinations. Okay. So, as I run my loop after k iterations, I should have k nodes in the set n prime, and it tells me that for those k nodes I know the least cost path. Okay. But you need to do further iterations till all the nodes that are there in the network belongs to n prime, because n prime is the set that we are trying to build grow, right. As more and more nodes are added to n prime, we know the least cost path to them for sure, right. So, definitively known means for sure, right. We okay. Uh, okay. So, these are the notations C, D, the predecessor node, and n prime. Now, let us look into the algorithm. Okay, algorithm, and I am also going to pictorially give you demonstration of how the algorithm works with an example as well. So, there is an initialization part. We have our network graph, right. In my router, I have the network graph, and I am going to find out the least cost path to all the different nodes from myself, and I will initialize the algorithm, and n prime, look at each one of these numbered lines in the syntax in the pseudocode. So, n prime is equal to u. Okay. So, I am trying to find out the least cost path to all the nodes in the graph from u. Okay. So, if you want to go to yourself, you are basically at the destination directly, right. So, n prime is equal to u, that is the initialization, because the shortest path to u is through you yourself only. After that, please take a note, for all nodes v, if v is adjacent to u, which basically means that I am going to consider the first of neighbors of u, right, and we update this dv is equal to c of u comma v. Okay. What is dv? dv was the cost to reach a node v from the source u. Okay. So, since this all the nodes are adjacent to u, which basically means that these are the direct neighbors of u, that is the cost that you can get till now, right, because you have not explored the full graph yet. It is an initialization. I am only updating the direct neighbors of u, which are all the set in the set of v. So, v is adjacent to u. So, dv is updated by the cost of c u comma v. Else, if you do not have a direct path, dv is equal to infinity. That is the initialization, right. Now, I have to run the algorithm. So, these are the initial estimates and just the link costs of the neighbors. Please understand that the shortest path to the neighbors may not be the direct path. Okay. So, please keep that in your mind in parallel. Let us say you have u, and the direct hop neighbors are, let us say v1, v2 and v3, right, and initially you update this cost. Okay. That is it, your dv, right. At this current moment, what is your estimates of the cost, right. So, there is one cost here, some cost, here you have some cost, here also you have some cost, but these are not guaranteed to be the minimal cost, right. In order to reach v2, this may not be the shortest path. Okay. There might be an alternate shortest path, which is either through v1 or v3, you do not know. At this point, this is your initialization and this is your best guess. After that we come to this loop where find W which is not in n prime, that is clear, right, because if you are putting a node inside n prime, this means that you definitely know the shortest path to that particular node. So, we are only looking for the W's which are not in n prime. So, find W which is not in n prime such that dW is a minimum. What is dW? dW is the cost of the path from your source to W, okay. And if it is minimum, I should be putting my node W to n prime, okay. So, this is what we have to do. So, the least cost among all the estimates, okay, because there cannot be a better estimate, okay. If you look into even this example, I will draw it in a bigger form, okay. Let us say you have U, you have V1, you have V2 and you have V3, okay. This is one path, this is another path and this is another path, okay. Initially you probe the neighbors, right, and let us say you know the distance here is 3, here this is 4, here this is 7, okay. Now consider that what is the least cost to V1, what is the best route to V1? The best route to V1 has to be this direct link whose cost is 3. There cannot be any other path to V1 with a cost less than 3, okay. If you think that, okay, I can reach V1 through the other paths, right, because there are only 2 alternates, right, I can from V1 from V2 I can go to some other nodes, right, and then ultimately come to V1, or I can come from V3 and then go somewhere and then come back to V1. None of them are going to be optimal because this 4 is greater than 3 as well as 7 is greater than 3, okay. And note that Dijkstra's algorithm is going to work on a network graph with only non-negative edge weights. If your edge weights are negative, this argument is not valid, because later you can have a very negative edge weight which is going to bring down the total cost of the link, the total cost of the path, right. Here we are only considering positive values of weights, okay. So, once I have seen this is 3 and here you have 4 and 7. So, the cost to V1 here should be at least 4, greater than equal to 4. If you have 0 for the rest even, right, it should be at least 4. Here through V3 it should be at least 7, right, at least 4, at least 7. So, at this point I definitively know that if I want to reach V1, the cost of that path is 3, okay, and this is hierarchically applied again and again, okay, but that is the crux. So, find W which is not in n prime such that dW is a minimum, add W to n prime, okay. So, we can add V1 here to n prime, update dV for all adjacent for all the V adjacent to W and not in n prime, okay. So, because it is not just the first hop, you are going to have other hops as well, right. Here it is going to continue, let us say some V4, there is V5, V6 and so on, and then you can have different kinds of network connections, right. I do not want to kind of discuss this right now for a particular graph. Whenever we are going to come to an example, we are going to see this in details, but this line should be clear to you. Update dV for all V adjacent to W, because now W is added, W is the new member in the n prime list. So, if I know that my least cost path to V1 has a cost of 3, right, somebody else could use it to update the paths to other destinations knowing the minimum cost till through dV, right. If there is something that is better, dV could be updated. So, dV for all the adjacent edges to W and not in there. So, dV is equal to minimum of dV, which was your current estimate, comma dW plus C of W comma V. Okay. So, whether the direct path to V, whatever is the or the path to your current estimate of the cost to V, whether that is minimum, or you have a new route to V via W. That is why it is then via W. So, you have to go to W. So, dW, you know, W is already in the n prime list, right. So, dW you know, right, and then you add this cost of C V comma W, because this is already there is a link that is there in between V and W. So, you can take this alternate path through W. So, this is a decision that you have to make and then see which one is minimum and update dV accordingly. Okay. So, again I am repeating, I have to update dV, which is the least cost path length or the cost of the path length to reach V. Okay. So, I have my current estimate, which is called dV. Okay. Now, I am trying to brainstorm, I am trying to think that, oh, I may have an alternate path to V via W. Let us not directly use this estimate called dV. Let me go to W and then take a path which is W comma V, that link. Is it going to give me a better path or not, right. So, for that we compare these two numbers, which is dV, the other one is dW plus C of W comma V, right. There is also a path to V via W. Okay. So, whichever is minimum, we should take that. Okay. So, the new cost to V is either the old cost, which was your already known cost, or the known shortest path to W plus the cost from W to V, which should be clear. Okay. This is called the relaxation step. Okay, you do not have to remember these names, but this is that is how this is called, until all the nodes are in the n prime set, because n prime we are basically going to add the nodes after each iteration. One node is going to be added until all the nodes are added. We are going to repeat this process. Okay. So, let us have a quick visualization of that algorithm. On the left hand side we have n prime, where nodes whose least cost paths from U are definitively known, and on the right hand side you have n minus n prime, where the nodes with estimated least cost path not definitively known to be the smallest possible. So, it may not be the optimal path, but we are in the process of finding out the optimal path. Okay. So, we have n prime, and this is on the right hand side n minus n prime. So, it is a set notation, that is why we are using this slash. Okay. So, n is the set of all the nodes. So, let us say U is there. I am basically trying to again capture the relaxation step, how exactly the updation step works. You have U in n prime. On the right hand side you have V, V prime and V double prime as these three destinations. Okay. So, now the question is whether you should directly reach V, right, through some other network of nodes, right, that is abstracted out, or you should use an alternate path through W. Okay. So, minimum cost in n minus n prime is of W, right. So, if you look at all the nodes in n minus n prime, dW is minimum, okay, which means that there is no other alternate path cost to W possible, because nodes are the edge weights are positive. So, you cannot go to V prime or V double prime or anything and then come back to W having a cost lesser than dW. Okay. So, minimum cost is basically dw, and you can add dw to n prime. Okay. Now, we should move w to n prime. Now, we have to do this relaxation step. So, for each v in n minus n prime, we ask this question: is the cost of the path via w smaller than the known least cost path to v? So, for we are at a certain stage in the iteration, right? If you remember the loop that we were kind of working on, right, this loop, and this is the loop that I am kind of referring to. Okay. So, at every step we are moving these w's to the n prime set, right, and also at the relaxation step we ask this question that okay fine, w is for certainly known, that I know that w is the candidate whose least cost path is known. Now, I have the other guys, right, where I am kind of not fully sure that whether the least cost path is known or not, okay, or the least cost distance, which is the dv, is known or not. Okay. So, what are you going to do? We are going to compare these two things, one is dv, the other one is the path to v via w. Okay. So, the cost of the path via w is smaller than the known least cost path to v. If so, update dw, and the predecessor of v is w then. So, if you want to reach v, you have to reach v via w. So, w becomes the predecessor node of the v. So, dw and cw comma v is the path, total path length or the path cost, and you have a direct path which is dv. Okay. So, dv is the direct path, dw plus cw comma v is the indirect path via w, and the cost of the base stone path is dv till now. Okay, till now it is dv, that is the red colored, this is dv. So, you compare them and choose which one is the minimum. Okay, and you can do it for all the other nodes v prime, v double prime and so on. If appropriate, you can update the belief that who is the right predecessor to reach these v primes and v double primes and so on. Okay. If your current belief is optimal, keep it. If addition of w, if the knowledge of the w shortest path could improve your beliefs, then use that. Okay. Hope this is clear. So, we are going to give a small example, and I am going to also give you one practice problem, and you can also in the instruction period the instructor could give you more problems and you should be able to solve this kind of problems, right, even for your assignments or exams. So, we again consider the same network graph that we have seen earlier. It consists of 6 routers and the paths are all given to you and the edge weights are mentioned. Okay. So, as you know that there are 6 nodes, right. So, by 6 iterations we should know the shortest path from u to all the other 5 nodes, right. So, suppose the source is at u, okay, we should know the shortest path from u to v, w, x, y and z. Okay. If you look at the different columns here, there is n prime. N prime is going to start from u and then expand to all, encompass all the nodes in the network, right. So, the final cardinality of n prime is going to be 6 and it is going to be starting from 1 initialization. Then there are these tuples which is dv comma pv. dv is the current estimate at that step, at the ith step of the algorithm, is going to be representing the distance or the least cost, okay, to v, and pv or pw or px whatever, right, that is basically the predecessor node. So, if you want to reach v, what is the previous node you should visit. Okay. So, with this let us start. So, we know how the initialization occurs, and in step number first step, the step number 0, initialization step, n prime is equal to is just only one element u, and then the direct neighbors. because remember in the initialization part we had two things, one was n prime equal to u, and the other part that we had to do was initialize the neighborhood list. So, the neighborhood list of u is v is one neighbor, right, w is uh, w is a neighbor, because yeah, we have a path, this carved path I missed out. There is this w is actually a neighbor of u, and then you have x, okay, this is also a neighbor. So, you can see this from this arrow, okay. So, v, w and x, the rest of the things are not neighbors, y and z are not neighbors of u. So, we initialize them with this infinity, okay, that is a 0th step, okay. So, now can you think at this step itself I definitely know the shortest path of one of the nodes, and which one is that? That is basically u, sorry, v, right, or x, because uh, as you see, right, 2 is the path cost for reaching v, right, w is the path cost for reaching, sorry, 5 is the path cost for reaching w, and 1 is the path cost for reaching x, right. So, here this dx is minimum, okay. So, I definitely know that if I want to reach x, you cannot beat this cost 1. If you look at 2 or 5, both 2 and 5 are greater than 1. So, it is not possible to have a cost to reach x which is lesser than 1, clear. So, 1 is the least cost here, and this should directly be added to the n prime set, okay. So, in the next iteration n prime is going to be u and x, okay. So, x is going to be tick mark, that I definitely know the path length from u to x, and the predecessor node is u. So, it directly from u, you have to go to x, okay. So, now with this knowledge, certain other things are going to be updated, okay. So, now at this stage your belief to v, w, y and z, we can see whether it can become better or not, right. So, if you look at v, okay, and their neighbors, is there a path through x that improves my estimation? Let us look at v, okay. So, v, you have a current guess of 2, right, and who are the neighbors? You have the neighbors like x, then w and y and so on. No, y is not a neighbor, x and w, and you can see that if you go via x, right, the cost is going to be 3, right. If you want to go to v via x, let me draw the path. Let us say you take this path through x, that is known to be optimal, and then c of x comma v, c of x comma v is 2, right. So, 1 plus 2, it is 3, and my current guess is 2. So, I am going to stick to my current guess, okay. I am going to stick to my current guess. Now, let us look at w. So, here we have w is under consideration. W, my current estimate is 5, and let us see whether I can do better or not, okay. So, if I approach through x, because x is, this is, there is a definitely better path, there might be a possibility through x, because x is known to be in the optimal set now. So, let us consider this path. If I go to x and I have a link from x to w, right, and x is in the n prime set, right. So, I can see that u x, that is 1, or basically dx equal to 1, and c of x comma w is equal to 3, C of x comma w is equal to 3. Okay. So, totally dw here is going to become 4, right, which is lesser than the current estimate 5, right. The current estimate was this direct link like this, which is 5, okay, which is greater than 1 plus 3. What is 1? 1 is basically your dx, and x is in n prime, and 3 is C of x comma w. Okay. So, 3 plus 1 4. So, I should not keep this belief that dw is equal to 5, dw is actually equal to 4 now. Okay. So, dw is equal to 4 now, and the predecessor node is going to be x. Okay. So, this belief is going to be updated, and this belief is also going to be updated. Similarly, for y and z, they are infinity. Infinity is of course the worst case, right. Now, I have a path till x, right, and x has neighbors which are your let us say y, right. Also we know the path to w, right. So, w has neighbors which is z, right. So, these numbers could actually be updated now. Okay. So, actually x is added, w is not yet added in the list. So, z is also still going to be out in the we still do not have a link to z yet. So, 1 is transferred. So, ux is there, 2u, and as you can see that 5 is updated to 4 and the predecessor node is updated to x. This part is done. Okay. And here we do not have anything to do because this is already in the n prime list. 2x is the new entity here, right. Earlier it was infinity, now it has become like this, that let me concentrate on x is x we are done. We are trying to now look for y, right. Y was infinity earlier, and now from through x I have a path to y. So, this is 1, this was known as dx, and now this is dx plus C of x comma y, which is 1 plus 1, which is lesser than infinity, right. So, we add the cost as 2 and the predecessor node as x. So, this is the cost as 2 and the predecessor node as x. Sorry for the confusion about z. Z is not yet going to be accounted for because we do not have a path to z through one of the nodes in n prime yet. Okay. So, we are going to do that. Now, we know about y, y's neighbor is z. So, later we will see in the next iteration. So, right now we can transfer y to the n prime list. Okay. So, you can do this. So, n prime will become u, x and y. So, once we do u, x and y, as you can see there are more updates. Let us look into those updates. This is done. So, x, y, u is already there. Now, let us look into w again. So, if you have this belief of 4x, now I have added y to the n prime list. I know that dy is equal to 2, okay, dy is equal to 2, right, and C of y comma w is equal to 1, right. So, my previous belief dw was 4 and predecessor of w was x, right here. After this I am asking, can I reach w via y, right, for the shortest path? The answer is yes, because you can always reach, but whether it is the shortest path or not we need to see. So, for that what we need to do? We need to see that dy plus C of y comma w, right, is greater than or lesser than the current dW. Okay. If yes, we have to update. So, now if we look at dW's value, it was 4, right. This was 4, and dy is definitively known because y is in n prime, this is 1, y comma w is also I think 1, y comma w is also 1, sorry, dy is 2, sorry, dy is 2, this is 1, okay. So, together this is 3, right, and if you look at this is basically lesser than my current estimate. So, that is why it becomes 3, okay, and the predecessor node becomes y. So, you have to reach w, this is the optimal path now, u, x, y and then w, the predecessor node becomes y, okay. So, y is updated now. So, from x it has become y, from 4 it has become 3. For z it was infinity. Now, let us get into the discussion for z. So, z was infinity, right. Now, from y I have a path to z. So, dy was 2 and y comma z. So, dy was 2 and c of y comma z is equal to 2. So, dz should be is equal to dy plus c of y comma z, which is equal to 2 plus 2 is equal to 4. Of course, you compare 4 with infinity, 4 is smaller. So, you update it by 4 and the predecessor node is y, through y I am reaching z, clear. So, now which is definitively known 2, right, you can't. So, all the other shortest path is either 3 length or 4 length till now. So, this is going to be now put into the n prime list. So, it will become u, x, y and v, and see we can't do anything better here. There is no other better path. You can always try to see by comparing their own neighbors, but you do not find a better path, you do not find a better path here either, right. And then this comes and then this comes eventually. So, this basically is going to give you the shortest path idea. So, if you want to reach a particular destination w or x or y or z or whatever, you get two things here. You get what is the length of the path. The other thing that you get is what is the predecessor node. Okay. So, predecessor node from your destination, right. From this we need to construct the forwarding table. Okay. So, remember we talked about this Dijkstra's algorithm, and after the Dijkstra outputs this table, we have to create the forwarding table for the router. Okay. So, our work is not done yet. In order to reach the destination z, I know that the cost is 4 and the predecessor node of z is y. So, this much I know, if I want to reach z from u, the total cost is going to be 4, that is correct, and the previous hop, this is your predecessor or previous hop, this is going to be y. Okay. So, this much is known. From here I need to construct this path, and if I am x, if I am myself x, I should be able to know that okay, my next stop is y, or I am here u, I should be able to know that in order to send the packet to z, my next hop is x. Okay, my next stop is not v or not w, my next stop is x if I want to send the packet, this is the destination. Okay. So, we have to construct the forwarding table now. To find the router port to use for a given destination, find the predecessor of the node iteratively until reaching an intermediate node, immediate node of the source u. So, I am going to tell you what exactly is going to happen. You know, to reach z, your predecessor node is y, right. So, you know that to reach z, you have to come from y. Now, if you see y and your cost was 4, here now if you look up y, you have to reach y, right. In order to reach y, your cost is 2 and your predecessor node is x. Now to reach x, your cost is 1 and your predecessor node is u, right. How are you getting this? For z you are getting from this one, right. For y you are getting from here, so you are getting from here. For y you have to come from x, so x details are here, right, and here you directly go to your source node, u is your source node. Okay. So, this is how you construct the forwarding table. So, u knows that in the routing table entry, if the destination, for this is for u, if the destination and the next hop, right, next, um, if the destination is z, next hop should be x. Okay, this is exactly what we try to tell here. The port connection to u to this neighbor is the output port for this destination. Okay. So, here again same example, dz pz we know is 4 comma y, okay, and z pz is y, and then py is equal to x. So, the predecessor node of y is equal to x, okay, I have told you already this, and the predecessor node of x is u, okay, and x is an immediate neighbor of u. So, it is a direct connection between x and u. So, this is your next forwarding table entry, that x should be your next hop neighbor if you want to deliver the packet to z. So, the forwarding table, if the destination is z, the link that you are going to utilize is u comma x. This is your forwarding entry, okay, or this is the port of your router. One of your router ports, u is the router, one of the router ports is connected to x, you should forward the packet to that particular port. This is the table that is maintained in a router, okay. And please note that this computation can run every now and then. We are studying link state routing. So, the network graph can change from time to time, and there is this flooding messages that are sent, the link state advertisements. So, the link state database keeps on updating. So, if your link state database keeps on updating, from time to time you can update your forwarding table, okay. So, if your forwarding table is optimal enough, you should be able to do the shortest path routing. That is how the routing can take place using link state routing. So, one practice problem which is looks a bit more involved here, I have in some cases directed links. So, from v to y I have a link cost of 4, whereas from y to v I have a link cost of 6, okay. And in some cases it is not that. I request you to have a practice exercise of building the table that Dijkstra's algorithm gives you, starting with the source S, right. So, this is your source node, okay, and from the source node you should be able to write that table, okay. And there are many other practice problems over the internet from the past, GET questions, right. There are various kinds of interesting questions on this link state routing. You should find some of those questions and try answering them, and the instructor, you can also discuss with him what kind of numericals you should be able to solve, right. You can ask for some more numericals. So, summarizing link state protocol, each router announces the link state to the entire network using flooding, right, that is the link state advertisements and the link state database part. Each node independently computes the least cost path to every other node using the full network information, okay. So, after flooding and populating the link state database, each node or router is going to create an estimate of the entire network graph, and then each router is going to independently run Dijkstra's algorithm on that network database, right. independently, okay, and the least cost path is going to be computed, and the Dijkstra's algorithm can efficiently compute these best paths, okay. Each and easy to populate a forwarding table from the predecessor information computed by the algorithm. So, the algorithm also gives you a byproduct of not only computing the least cost, but also in order to achieve the least cost, what is the predecessor node. So, that information is extremely important for us to construct the forwarding table, okay. So, keep that in mind, and that is it for the link state protocols. Next we are going to look into the distance vector protocols, okay. So, link state protocols was uh, kind of having a global information of the network graph in each router. The communication overhead is expensive, the communication overhead is very high because the messages are flooded across the network, but it gives you the complete picture, okay. Every node has a complete picture of the entire network. Distance vector routing protocols has some other issues, although it is cheap in terms of communication overhead, but there are other issues that we are going to see what happens there, okay. So, next we are going to look into distance vector routing protocols, okay.